Well,
hello everyone, I'm Siyuan. Thanks for coming this early. Apparently my conspiracy of setting this up really early didn't actually stop you from coming, so that's good. So today I'm going to talk about the thesis work I did, which is using hierarchical optimization to do online control for a humanoid robot. And this is a quick video of the DARPA Robotics Challenge. So in this challenge, we programmed the Alice robot, which is this guy, to do a bunch of walking and manipulation tasks. So here it's turning a valve. It would just walk past the door, and it has to, in this case, turn on a power drill so that it can cut in that wide piece of sheetrock later on. So a lot of all these manipulation tasks, they are very heavily teleoperated, which means there's an operator sitting behind a camera feed and trying to tell the robot what to do next. So here is the robot doing another manipulation task, which is trying to flip this circuit breaker. This task is actually done completely teleoperated. So here the robot is doing a walking task. It has to traverse this strip of cinder blocks. This one is actually a little bit more automated in the sense we use the laser rangefinder to build a map first and then do footstep planning and then have the walking controller go over that. This is the last task at the DRC, which is climbing a standard staircase, and that's the finishing line there basically. So after DRC, we did a quick experiment trying to see how fast we can push the DRC walker to, and that's about the walking speed we have. It's about 0.4 meters per second. Oops. And also here is some kind of safety features we implemented during the DRC, basically to catch unexpected scenarios. A lot of them involves establishing contacts that we didn't really plan for, and how to pause the controller from killing itself, and then the operators can take over and have a chance to recover from these scenarios. So this is the very brief sort of a highlight for the control part for the DRC challenge. Now, for the Alice robot, it's a humanoid built by Boston Dynamics. It's a pretty big robot, about 180 kilograms heavy. It has 30 actuated joints, 6 for each leg and 7 for each arm. Most of these joints are hydraulics, except 3 harmonic drives at the end of each forearm. Also, the neck pitch joint is also electric. So, for the DRC finals, the robot has to be completely tetherless, so it needs to carry its own power. In this case, it's a very heavy battery pack, and all the computers, all the sensing as well. In terms of the E-box or the joint level controllers, everything can be sensed and commanded at 1 kilohertz, so that's the lower level control loop frequency. In terms of sensing, we have a sensor head built by Carnegie Robotics that has a laser rangefinder and a pair of stereo cameras on it. For the actual joint sensing, we have LVDTs that's measuring the piston positions for the linear pistons, linear hydraulic actuators, and also we can measure the forces by pressure sensors. We have a really good IMU built by KVH. It actually greatly simplifies our state estimation technology, which is good. In terms of force torque sensing, we have 3 axes at each foot. We can measure the vertical force and the 2 moments. And for each wrist, we have the 6 force torque ATI sensor mounting at each wrist. So that's briefly the sensing capabilities we have. Later on, we added some custom sensors. So you probably heard about those from Ben X's talk. Okay, so here's a sort of a quick outline slide for how this talk is arranged. Firstly, go over some introduction stuff, and then because my title is Hierarchical Optimization, So naturally, I need to go through each hierarchy and talk about what I do and what they're supposed to do. And then I'm going to do a slide or a couple of slides on future work of what I think is still needs to be solved so that this technology can be actually used for doing real stuff. And then last but not least, the conclusion slide. So to motivate or to sort of put into the scope of this talk, I want to briefly talk about dynamic programming first. Considering a dynamic system, we have state X, and for each state we can have a set of actions we want to take. It's represented by A. And then we have a state transition dynamics function, F. And we can also define a one-step cost function, L. So with all these things defined, we can introduce a concept called value function. And essentially, it's a notion that captures how good each individual state is, considering all its best possible future evolutions. So once we have this value function, it's very easy to exploit it and use it to generate an optimal policy, which is essentially for every state, what you do is you look at the action that gives you the minimum sum of the one-step cost function plus the value function evaluated at your next state. So value function is good. Once we know value function, we can do optimal control. That's the basic idea for this slide. And for all my hierarchies, I use this value function in sort of a top-down approach. Basically, I compute it at a high level, and then I push it down to the lower level optimizers so that they will have an idea of what the top-level guy wants to do eventually. So this is kind of a pyramid representation for a typical walk-in system. So in this case, for a humanoid robot, a very popular way to make it actually walk and useful is have some kind of a footstep planner in the first place to plan for a set of footsteps to bring the robot from wherever it is to wherever it wants to go. So that's represented by this A-star triangle here. For our system, we think it runs roughly at 0.1 hertz. And then the top level in my controller actually is a trajectory optimizer block. What it does is it tries to fly a center of mass trajectory, fly it through this set of footsteps using a simple model. And for me, this runs about 1 hertz. So it happens every time the robot puts a foot down, it plans for the next couple of steps to generate the center of mass trajectory. And then the next level down is what I call a receding-horizon block. The idea for this guy is trying to run it as fast as possible, but then it doesn't have to look as far into the future. So it can only, it only needs to look into maybe the next 100 milliseconds. But what it's trying to do is generate a short trajectory or fix the original plan so that it's dynamically feasible. And then the bottom level is something that translates all these Cartesian motions into things I can apply on the joint level controllers. So what it does is translate the center of mass motion, translate the swing motion, the hand maybe, translate them all into joint level commands such as torques, positions, or velocities. And this guy runs about 1 kilohertz, so it runs as fast as the robot's lower level controller. And as I said, I compute this value function approximation in the top level optimizer and try to push it down all the way to the bottom layer. So the high level idea for this talk is to find a balance between how far you look into the future and how complex a model you use. So at the top level, I plan for a long horizon, but because I can't afford to do full dynamics, otherwise it would be too slow to run it online, so I have to constrain myself to a simple model. But as I go closer to the actual robot, to the actual hardware, I start to consider more dynamics, more constraints, but, ooh, I shouldn't play with this thing. But then I can't compute as far into the future, so I have to do a shorter horizon. So, In terms of related works, I break it down into three major parts. There's been a lot of work on generating the center of mass motion using point mass models. The most famous one is probably the preview control proposed by Kajita. And also, Jerry Pratt's group has done a lot of work on using capture points concepts to do walking motion generation as well. In terms of receding horizon control, there's been many formulations. So for the first one by Urata from JSK at Tokyo University, the basic idea is to extend the cost function in the preview control so that it can be, with a special form, it can be generated really fast. The center of mass trajectory and the ZMP trajectory can be computed really, really fast. So they run that inside an optimizer to figure out what's the optimal foot placement online. And Pierre Weber's group has done a lot of work in trying to formulate a walking pattern generation as a linear MPC. And then they extended this further to, for example, reaching a goal into the future, and also some 3D walking examples as well. Also, there's a lot of work by Ben Stevens on using NPCs for standing balance and sometimes walking as well. So my version of the NPC is formulated more similarly to Pierre Weber's and Ben Stevens. In terms of the full body controller, a lot of people do it as a sort of a full body inverse dynamics approach. This is all motivated by Osama's work on the operational space work. And my formulation is more closely to the second one, which is using a weighted objective function. But also there's a lot of interest in trying to impose a strict hierarchies on different objectives you want to achieve in inverse dynamics. So there's that. Okay, so the first part in my controller is to generate a center of mass trajectory. And the way I look at it is I try to do a trajectory optimization, which is essentially minimizing the state deviation and also the center of pressure deviation from a given nominal or given desired trajectory. So this desired trajectory doesn't have to be physically correct, it's just a preference of what I wanted to do. So for this part, I'm using a nonlinear point mass model. It has the x, y, and z dimensions in it. So in retrospect, when I look at the data after DRC and also doing the fast walking data, the z dimension actually doesn't help that much for robustness or performance. But this is still a good example because we can use nonlinear dynamics in it. We can potentially push this to including angular momentums, which I think is going to be much more useful in this case. For me, I'm planning for the next 3 footsteps into the future, and I'm using a technique called differential dynamic programming. It's an iterative local trajectory optimization technique. At the end, it gives us a local optimum for nonlinear systems or non-quadratic cost functions. Aside from the optimized trajectory, it also gives us local approximations for the value function and also a linear optimal policy along this trajectory. So I'm replanning, rerunning this process every time I take a new step. So that's roughly on the order of 1 Hertz. So here's a cartoon version of how DDP works. Basically, it's a trajectory optimization technique, and it's iterative. So we have this initial trajectory first, and what we do first is to run a backward pass that propagates the value function's spatial derivative backwards in time. So these guys are the derivative of the value function with respect to the state. And then what we do is we use these derivatives to generate a change in the command, which is this delta u. And then we can run this updated control to get a new trajectory, which is this one. And this new trajectory will have the lower value function. And if we iteratively do this process, it will converge to a local minimum, and that's where we stop. At the end, we have a value function approximation that looks like this. So it's a quadratic It's a quadratic optimization. It's a quadratic approximation, and also we will have a linear policy that looks like this. So LQR is a simplified version or a special case for DDP in the sense that the system is linear and the cost is purely quadratic. So if you run it for a point mass model, this is what it looks like. The red ball is the point mass, and it's hitting a bunch of targeted footsteps. If you look at the plots, here I'm plotting the x, y, and z versus time, and the last one is the top-down view of the xy plane. So the desired footsteps, they're given as these red, as the red trajectory, which you can barely see. So these desired center of pressure is, in this case, specified by a square wave that's going through all the desired footsteps. And the green one is the optimized center of pressure, which in this case is very closely to the desired one. And the planned center of mass trajectory is what you would expect from a typical sort of a walking pattern generation from a LIPM or similar approaches. So now I've done the center of mass trajectory optimization for the next 3 steps. A lot of the times when we are doing walking, the center of mass state doesn't actually track the plan very well. This can be due to bad control, for example, or if somebody kicks the robot or bumps into something or it steps on something it didn't thought it's going to, the foot starts sliding, things like that. Essentially, the original plan becomes not invalid. So the controller physically can't track the original plan anymore. And in this case, we need to come up with some new plan or some new trajectory to be dynamically feasible. So part of the main incentive for this foot placement controller is trying to figure out where's the best next foot placement so that the center of mass trajectory can get back to the original plan as closely as possible in the future. So that's the motivation for this part. But in order to make this thing run as fast as possible, I have to make a couple assumptions and fall back from the nonlinear dynamics. So in this case, I'm using the linear inverted pendulum model for the dynamics. It is a linear model, and together with a fixed step timing assumption, all the future evolutions for the center of mass state is linear with respect to the center of pressure. So that makes the optimization a convex problem and can be easily solved very fast. Also, I made a point foot assumption. So this one is trying to essentially coincide the center of pressure with wherever I put the step. So I don't have to discretely sample the center of pressure trajectory. Instead, I can just say wherever it puts the foot, that's where the center of pressure is going to be. You can sort of relax this part by introducing a piecewise linear or a constant function for the center of pressure. So we have a little bit more variables to optimize for, but that's not too bad. So after I did everything, I can run this controller at 500 Hertz. It can probably go faster, but this is how fast the image dynamics runs anyway, so it doesn't buy me much if I run it at a faster rate at this point. This foot placement controller is formulated as a quadratic program, and this is the sort of canonical form of a QP. So we're minimizing the quadratic cost with respect to this curly X thing here, subject to a bunch of constraints, linear constraints that can be inequality or equality constraints. So with the assumptions I just talked about, the state X here is a linear function with respect to the center of pressure, which is also the foot placement. So X looks something like this. And the QP setup is actually very simple. It has a function that's minimizing a 2-part sum. The first part is penalizing the state deviation, which is X with respect to X star. And that's weighted by this value function, or the Hessian of the value function approximation. And the second term in this cost function is a term that's penalizing deviation from the actual foot placement to a desired foot placement P star here. So for the state trajectory tracking part, X star, this VXX is coming from the DDP or the nominal plan. And this P star, the desired foot placement, and this W, which is a weighting term, these two guys, they come from the footstep planner. Excuse me. In terms of constraints, I can use convex hull to approximate linearly what's the allowed region for the next foot placement. So these constraints, they can potentially come from the footstep planner as well. So in an idealized world, the A star planner not only tells me whereas P star was the desired foot placement, it also tells me if I want to vary it a little bit, how much cost I need to pay to vary that footstep, and also what's a allowed region for the varied footsteps. So in this formulation, I did it only for the immediate footstep, but you can easily extend it to multi-step strategies because, again, the dynamics is linear with respect to the optimization variables. So here's a simulated MATLAB example. The top row is the center of mass position. This is the velocity. This is the actual center of pressure trajectory and the swing foot and the actual foot placement and the current stance foot. So here in the second plot, the center of mass velocity is perturbed by 0.2 meters per second, completely arbitrary up.